Welcome to the inverse Laplace transform of a product. So just a little bit of motivation for why we want to do this. Note, if we have an IVP, of the form a y double prime plus by prime plus cy equals f of t with initial conditions y of 0 equals 0 and y prime of 0 equals 0. Then we, taking the Laplace transform, we get a times s squared capital Y of s minus 0s minus 0 plus b times s capital Y of s minus 0 plus c times capital Y of s is equal to capital f of s, the Laplace transform of f of t. And this just simplifies to the characteristic polynomial as squared plus bs plus c times y of s equaling f of s. And so we have y of s is equal to 1 over as squared plus bs plus c times f of s. So if we call this 1 over as squared plus bs plus c the function g of s, then we have capital Y of s is equal to a product f of s times g of s. And y of t is the inverse Laplace transform of the product f of s times g of s. So what we wind up getting is that we can essentially, using the inverse Laplace transform of a product, we can find the formula for y of t no matter what our function f of t is. So if we knew the Laplace transform of a product, the inverse Laplace transform of a product of functions, then we could develop a formula. Then we could create a formula for y of t, which is essentially based on f of t. So if we have sort of the set homogeneous equation, but our f of t can be various different things, we change the external force. We can just create a formula so we don't have to solve our IVP over and over and over again. So this is kind of a motivation for why we want to know the inverse Laplace transform of a product. So the theorem we're going to work with is the inverse Laplace transform of capital F of S times G of S is equal to the integral from 0 to t of f of tau, lowercase f of tau, times g of t minus tau, d tau, where f of t is the inverse Laplace transform of capital F of S, and g of t is the inverse Laplace transform of capital G of S. So this exists assuming those inverse Laplace transforms exist. So note, this is equivalent to saying that the Laplace equivalently the Laplace transform of the definite integral from 0 to t of f of tau times g of t minus tau d tau is equal to f of s times g of s. So we're going to do sort of a rough sketch of the proof. It's not going to be extremely formal. I'm going to leave everything in improper intervals. So just working with a rough proof, or the proof idea. Let's go ahead and just take the Laplace transform of the definite integral from 0 to t of f of tau times g of t minus tau d tau. So this, by definition of the Laplace transform, this should be the definite integral from 0 to infinity of the definite of e to the negative st times the definite integral from 0 to t of f of tau times g of t minus tau d tau and then dt. And this should be equal to the definite integral from 0 to infinity of the definite integral from 0 to t of e to the negative st times f of tau times g of t minus tau d tau dt. We are going to go ahead and reverse the order of integration. So reversing the order of integration. The region that we are currently looking over, we are allowing t to run from 0 to infinity. And then tau runs from 0 to t. So we take the line tau equals t, and tau can run from 0 to t. So we are looking at the region below the line tau equals t. So if we reverse the order of integration, if we do tau as our outside and t as our inside, this becomes the definite integral from 0 to infinity for tau. But now t will run from tau to infinity, since we're looking to the right, not the left. I need to update my screen, I apologize. So again, if we let tau run from 0 to infinity, our t then will be running from tau on to infinity instead of from 0 to tau. Then we have e to the negative st times f of tau times g of t minus tau dt d tau, reversing our order of integration. Since we are integrating with respect to t first, we can pull that f of tau outside of that inside integral. So we have the definite integral from 0 to infinity of f of tau times the definite integral from tau to infinity of e to the negative st g of t minus tau dt d tau. So now we're going to do a slight change of variable. So changing the variable or doing substitution, let's go ahead and set x equal to t minus tau. Then we have dx is just dt. And we also have that t is equal to x plus tau. Furthermore, t equaling tau. So for our bounds, if t equals tau, then x would be equal to 0. t being infinity, x will still be infinity. So our new definite integral, we have the definite integral from 0 to infinity of f of tau times the definite integral from 0 to infinity of e to the negative s times t is now x plus tau, and then times g of x dx d tau. That inside integral, we can pull out an e to the negative s times tau. So this is definite integral from 0 to infinity of f of tau times e to the negative s times tau times the definite integral from 0 to infinity of e to the negative sx g of x dx and then d tau. This definite integral from 0 to infinity e to the negative sx g of x dx, that is precisely the Laplace transform of g of x. So this would be just capital G of s. So we are looking at the definite integral from 0 to infinity of f of tau times e to the negative s times tau times capital G of s d tau. Again, rewriting this, g of s is independent of tau. We can pull it out front completely. We have a capital G of s times the definite integral from 0 to infinity of e to the negative s times tau, multiplying f of tau, then d tau. This definite integral from 0 to infinity of e to the negative s tau, f of tau d tau, is just the Laplace transform of f of tau. So this is capital F of s. And so we therefore get that the Laplace transform of the definite integral from 0 to t of f of tau times g of t minus tau d tau is indeed equal to capital F of s times capital G of s. So this particular integral comes in handy just because it is the inverse Laplace transform of a product. So again, similarly, the inverse Laplace transform of f of s times g of s is the definite integral from 0 to t of f of tau g of t minus tau d tau. So that is sort of, again, our rough sketch proof. We did some changing of or reversing order of integration and dealing with improper integrals that we would need to make a little more formal officially, but this is kind of the idea behind the proof. Just for some vocabulary, we call this definite integral from 0 to t of f of tau g of t minus tau d tau the convolution of f and g. And in terms of notation, we write f and then a little asterisk g as the convolution is evaluated at t is equal to precisely that definite integral from 0 to t of f of tau g of t minus tau d tau. So if you hear or see convolution or see this notation f asterisk g, this is what they were talking about, and it is just the inverse Laplace transform of that f of s times g of s.